Greetings, my name is Marty Hudson, and I'm going to be presenting a paper on the historical progression of the Los Angeles Metro seismic design criteria. This is a paper co-written with Jeff Martin and Andrush Danielians. I will give the first part of the presentation and Andrush will continue. We're going to be talking about the timeline and how things have progressed all the way from 1924 to the present day. So we're going to see these steps in progress. The oldest portion of time is 1924. Not many people know there's a tunnel that still exists through much of LA, a little more than 1 mile in length, that was operated until 1955. So the question is, how was that seismically designed at the time? It probably wasn't. There were probably not many seismic considerations for design of that tunnel. Then we move forward, and Los Angeles had a number of proposals for mass transit systems, some underground, some above ground. This was in 1968, and it's a system that wasn't built, but nevertheless, the designers at the time knew that they should look at seismic forces. So they utilized the provisions from the Structural Engineers Association, that's called the SEOC Blue Book, which is the same provisions that worked their way into the Uniform Building Code at the time. The modern rail era began in the late 1980s, and these are the trains that still run today, the Blue Line and the Red Line. And the Blue Line was constructed by the LA County Transportation Commission, and that line included a 0.6 mile tunnel under Flower Street, which is still used heavily. And the Southern California Rapid Transit District designed and built the Red Line, which had their initial line was 4.4 miles through downtown LA. Both of these were designed and constructed about the same time. Those two agencies are now merged in LA County Metropolitan Transportation Authority. So how were these tunnels designed? At the time, the RTD relied heavily on some recent work that had been done for BART, the Bay Area Rapid Transit District, in the late 1960s and early 1970s, and research Peck had done on performance of underground tunnels in seismic conditions. So with that research, one of the big considerations was what design levels for shaking could be considered. And the two-level approach was adopted, and that still is used today. The lower level is the more frequent earthquake every 150 years, called the operating design earthquake. In that frequent earthquake, we want the system to continue performing well with little or no damage. Then the high level is a 2,500-year recurrence called the maximum design earthquake. And for that earthquake, you want to preserve life safety. So even if you have a little damage in the tunnels, nevertheless, you want everyone to get out safely. So with the two-level approach, then we consider the various seismic hazards, which include fault rupture, shaking, deformation, and other geologic hazards. The shaking results in racking deformations. The earlier analysis and design, like in 1984 with Monsees and Merritt, was to consider designing underground structures to conform to the free soil deformations. However, that's pretty conservative, and they knew that at the time. The modern seismic design criteria, after those initial lines were built, are contained within the Metro Seismic Design Criteria. Here's what it looks like, and in particular, in section 5 of that guide are all the criteria for above grade, at grade, and below grade structures. There's also an appendix to that section called the Metro Supplemental Seismic Design Criteria, and that gives a high level of detail and background for seismic design of underground and above ground structures. Going back to fault rupture displacement, that cannot be entirely avoided with the metro system because the tunnels and other lines have to run a long distance. So where they cross a fault, and if that fault is active, Holocene active, then you need to carefully determine what the hazard is. Tunnels can be designed so that they don't collapse where they cross faults, but underground stations, the mitigation where it crosses a fault is to locate the station away from the potential displacement to keep people safe. There's similar mitigations for above grade structures from the displacement of the fault. Finally, the ground motions, are highly detailed in how you develop the ground motions for both of the levels, ODE and MDE. They currently use basin effects and near source effects using Caltrans methodologies to modify what otherwise would be obtained. Finally, I wanted to point out that vertical ground motions are now required to be considered in the design of underground structures, either with pseudo-static methodologies or a full three-dimensional model. Other geotechnical hazards need to be considered, like liquefaction, landslide, and other strength loss phenomena. So now I'm going to pass it over to Andrew.
Thank you, Marty. I will discuss the evolution of requirements of seismic design of underground structures here in Metro. The seismic waves can cause ovaling and racking on underground structures. These are due to upward passage of seismic waves. Seismic waves can also cause snaking and deformation on underground structures, which are caused by horizontal progression of seismic ground motions. The inertial effect on structural components might also be considered in the seismic analysis of underground structures, and the seismic shaking at the foundation level places demands on the above ground structures such as bridges and buildings. In 1993, Wang authored a report in which he stated that for racking analysis of rectangular underground structures, a free field method can be used to analyze the structural response. However, this may produce overly conservative results as the stiffness structure may deform less than the soft ground in which the structure is. So he introduced a stiffness ratio coefficient to reduce the racking deformation of the rectangular structure based on relative soil versus the box stiffness. An equivalent seismic load can then be applied such that predicted stiffness adjusted racking would be achieved. In here, delta S is the racking displacement of the structure. R is the racking displacement coefficient, based on the relative stiffness of soil and structure, and delta free field is the racking displacement that would occur in the free field over the height of the structure. In our 2012 seismic design criteria, two approaches were provided for analyzing ovaling deformations of circular tunnels. The first approach was a closed form solution based on procedures from Wang's 1993 report for evaluating relative stiffness of soil and the tunnel lining. The second approach required a numerical modeling. The first approach is only appropriate for a completely circular cross-section with uniform liner thickness, with no structural decks or walls inside the tunnel, relatively homogeneous surrounding soil, and no interaction effect from other tunnels or structures. So it's a very idealized situation. The second approach, meaning the numerical method approach, can be performed in one of three ways: pseudostatic, pseudodynamic, or dynamic. In 2013, revisions of our design criteria, the numerical modeling approaches were redefined for circular tunnels by removing the allowance for use of simple pseudostatic numerical modeling methodology. In 2013 revision, we also provided more guidance for utilizing a pseudodynamic approach and modified the dynamic approach as well. The pseudodynamic procedure for circular tunnels is decoupled and has two steps. One, perform wave scattering analysis with voids, and then two, input displacement time series through equivalent springs. For analysis of tunnels in highly variable subsurface conditions, a variable structural stiffness or variable structural stiffness, two-dimensional analysis would not be adequate. The analysis in this case would need to be three-dimensional, with ground motions applied to springs representing the surrounding soil. I will close the discussion on seismic analysis of the circular tunnels by providing you with the revisions we made in our design criteria in 2017. So the closed form solution based on procedures from Wang for evaluating relative stiffness of soil and liner could only be used during preliminary design. Numerical modeling approach was allowed, and 3D tunneling response was also allowed for the analysis of circular tunnels. Now let's move to the progression of design requirements for box structures. Similar to the analysis methodology for circular tunnels for underground box structures, seismic analysis was specified in 2012 metro design criteria as either being semi-closed form solution, which requires simple conditions consisting of one, structures of rectangular cross-sections shaped, relatively uniform surrounding earth medium, and negligible soil structure underground interaction effects from nearby structures. And two, numerical modeling approach. In the 2013 design criteria, the rectangular box structure analysis technique were modified, specifying them in significantly more details. The methodology to be used was one pseudostatic that uses one-dimensional site response displacement snapshots applied through soil spring, simplified dynamic that uses one-dimensional site response displacement time series applied through soil spring in a dynamic manner, two-dimensional dynamic approach that decouples wave scattering approach using two-dimensional site response displacement time series applied through soil spring in a dynamic manner, and four, fully coupled dynamic model. In 2017 version of our design criteria, there was a revision to acceptable criteria such that the more simplified semi-closed form solution was considered acceptable for preliminary design only, and it could also be used for comparison with numerical modeling for final design, just to have a sanity check. This is a reflection and acknowledgement of the progress of numerical analysis techniques that have now been widely adopted in the engineering community and are at relatively minimum cost. For the simplified semi-closed form solution, either the computer program Deep Soil developed by Hashash or Shake 91 developed by Idris and Son could be used. In addition, when applying the racking displacement to the rectangular cross-section in the simplified semi-closed form solution, both a computational using a triangular force distribution and a concentrated force would be required. So basically two analyses need to be done, and the larger of those two will govern the design. In addition, the 2017 version of the design criteria specified that at least 7 time series derived from different recordings be utilized in the analysis. For the numerical modeling of the rectangular tunnels, the 2017 criteria eliminated the simplified pseudostatic and simplified dynamic method and added the three-dimensional fully coupled technique. The addition of three-dimensional fully coupled technique was once again was done acknowledging that the three-dimensional computational methodology has advanced to be feasible for metro analysis. Also, it's often necessary for proper analysis of station structures because one, underground stations have very different stiffnesses at the wall ends than from portions with no transverse walls. This results in varying responses along the length of the structure. And two, underground stations have several openings and appendage structures that modify the overall response and create points of increased or decreased stress at the interface of the appendage structures and the main station box. In 2017 version of the design criteria, we required that for station analysis, the impact of adjacent structure must be considered. Adjacent structures can be accounted for in 2 or 3-dimensional models. Significant research has been performed in the seismic design of underground structures with nearby structure in an urban setting, such as almost all of our projects. And the research has shown that the seismic effect of nearby structures on underground stations should not be ignored. This is a table that shows progression of our seismic design, our requirements for seismic design of underground stations. This also appears at the end of our paper that can be readily referenced. And that concludes our presentation.